So energy affects matter. And what do we mean by energy? In science, we talk about energy as being the capacity to do work. Let me switch my colors here from my previous class. The capacity to do work is energy. And work is not something that you get money for. Work is a force acting over a distance. So when I pick up this bottle of soapy water, I'm exerting a force over a distance. I just did work. Nobody specifically paid me money to do that, but it was still work. So we can come up with an equation like this. Energy equals work, which equals force times the distance. The greater the force, the greater the distance, the more work that's involved. Heat is related to energy. Heat is the flow of energy caused by a difference in temperature. I think we all know from just being alive that heat flows from warm things to cold things, and they tend to come to be the same temperature, right? Energy can be exchanged between objects through contact. For example, through collisions. So we have to get these ideas of energy, heat, and work straight. So it helps to think of energy as a quantity that can be possessed by an object, and heat and work are ways that that object can exchange energy with other objects. Okay, so energy is something the object possesses, and when it exchanges energy with something else, that's heat and work. Energy can move out of the object or into it. I think that in many ways, energy is like money. Money goes out of your wallet and money comes into your wallet, right? It can go either way. There are different kinds of energy. Kinetic energy is the energy of motion. So here we have an illustration of a pool table, and here we have the cue ball moving. It's moving, it has motion, that's kinetic energy. Thermal energy is energy associated with temperature. Thermal energy is a kind or form of kinetic energy. Because when an object is warmer, the particles in it are moving more. The particles themselves have greater kinetic energy. So even though that cup of hot coffee is not moving across the room, it doesn't appear to be moving to us, we know because of its temperature that the particles in the coffee are moving faster than they would in a cold soda. Potential energy, so there's two broad categories: kinetic energy, which has to do with motion, and potential energy, which is energy of composition and or position. So I usually have a pen. I don't have a pen. I can't do this lecture without a marker of some kind, because I have to drop it on the floor. So here's my dry erase marker, which is not useful in this classroom because we don't, I have a dry erase board right here. But anyway, that's a chalkboard. I don't like to drop chalk because it breaks. So this marker, if I hold it here, it has potential energy, energy of position. The other thing I like to think about is those Bugs Bunny cartoons. There was, dangling pianos out the second floor window, right? Why? Why were there so many pianos in the cartoon? Anyway, so what happens if I let go of this? It falls. As it falls, its potential energy is decreasing as it gets closer and closer to the floor. But its kinetic energy is increasing because it's moving faster and faster until it hits the floor. And what happens to that energy when it hits the floor? It becomes thermal energy. It's dissipated as heat. It's such a small amount of energy that you can't really detect it with just your senses, but it's there. So potential energy, energy of position, like hanging a piano out a second floor window. There's a lot of energy in that piano. If the rope breaks, it's going to come down, right? Chemical energy is a form of potential energy. This has to do with the relative positions of the electrons and the nuclei in atoms and molecules. And so the positions of those particles give it a certain amount of energy. It's potential energy. It's like something could happen. It's like waiting to happen. And so we can think of that as the composition part of potential energy.
Chemical energy?
Chemical energy. So gasoline, right, is a fuel. Why do we put gasoline in our cars? Because it has a great deal of chemical energy stored in the bonds in the molecules that make it up. And when you burn that, you release the chemical energy, and you can transform that into useful forms of energy, like moving the pistons in your car to make the wheels turn. And so then that makes you move and go down the road. So energy broadly as the capacity to do work. Kinetic energy, energy of motion. Thermal energy is a subset of kinetic energy, has to do with the temperature of an object. Potential energy is due to position or composition, and chemical energy is a subset of that. It's potential energy because it's associated with the positions of the particles in the atoms and molecules. So within potential and kinetic energy, there are many different forms of energy. There's electrical energy. This is a form of kinetic energy because it has to do with the flow or movement of electrical charge. This is electrons moving in a wire. Heat or thermal energy is kinetic energy with molecular motion. Light energy or radiant energy has to do with energy transitions in an atom, and we'll learn more about that later. Nuclear energy is potential energy stored in the nucleus of atoms. When you have a nuclear reaction occur, you generate tremendous amounts of energy, and those come from disrupting the nucleus of the atoms. Chemical energy we talked about is a form of potential energy. So the law of conservation of energy. Energy cannot be created nor destroyed. It can be transferred from one form to another, but the total amount present at the beginning is equal to the total amount present at the end. If you have a situation that appears to violate the law of conservation of energy, there's probably just a form of energy that's being overlooked. Here, there's an illustration of a woman pressing a ball down on a spring. And as she pushes down, she's imparting mechanical potential energy, compressing that spring. When she lets go of the ball, the spring unwinds and imparts kinetic energy to the ball. And so we get this transfer. We can have a transfer back and forth between kinetic and potential energy. If you think of someone swinging on a swing, see, I don't think we have a picture of that. I will draw you a bad picture.
So are these like, you know how you said there's heat and thermal energy, which is a form of kinetic energy? So are all of those playing out when you watch something like that happen?
Yeah, this is an interplay between potential and kinetic energy. Those are the two broad categories of energy, and then we have different forms within each. So if we think of someone swinging, so here they're starting here, and they're going this way and that way, and this way and that way. At the end of your swing, at the peak of your swing, you have the most potential energy because you're the highest off the ground. So at this point and at this point is your highest potential energy. And the fastest you're going is when you reach the very bottom. You come to the top of your swing and you stop very briefly, and then gravity pulls you down, and you're at your fastest right at the bottom of your swing, and then you slowly slow down as you go back up. And so when you're swinging, you're transferring kinetic energy to potential energy. Kinetic potential, kinetic potential. It's back and forth, back and forth. When we talk about energy, it's important to understand the system and the surroundings. The energy content of the universe is constant, but we're interested in energy moving from one part of it to another. And so we talk about the system and the surroundings. The system is defined as that part of the universe that we're interested in. It could be anything. It could be the whole building. It could be something occurring in my cup. It could be an atom. It could be my computer. It could be anything. It's defined, this is what we're looking at. That's the system. The surroundings is the rest of the universe, essentially. More practically, it's everything else with which the system can exchange energy. Because if we're thinking about the ice melting in my cup as the system, is that going to have any impact on the temperature of the air in New York City? No, probably not. It's probably only going to have an impact on a small area around it. But what we look at is the exchange of energy between the system and the surroundings. Energy is not something that we can measure absolutely. We can measure mass, but we can't measure energy. We can only measure the transfer of energy or the change in energy. So conservation of energy means that the amount of energy gained or lost by the system has to be equal to the amount gained or lost by the surroundings. It's a little bit like money. You know, if I pay you $5 for a burrito, I lose $5, you gain $5, right? Money doesn't disappear in that transaction. It goes from one to the other. And if I decide I want a refund and I give you the burrito back, then the $5 comes back. So whatever is lost by one has to be gained by the other. So let me make sense of this picture here. So here's the system and the surroundings. And so before energy transfer, here the system is half full and the surroundings is at 1/4. So if the system loses 1/4 of this gauge worth of energy, that energy has to go somewhere and it goes to the surroundings. We look at this with the system and surroundings, so there's always two parties. The system and the surroundings. So this 1/4 bar of energy that's lost here went to the surroundings. I don't know if that picture is helpful or confusing. If you have questions, please interrupt me. We need units of energy to measure it. The amount of kinetic energy that an object has is directly proportional to its mass and its velocity. So kinetic energy, which is generally abbreviated KE, is 1/2 the mass of the object times the velocity squared. And so the SI unit of energy is the joule. And the joule is 1 kilogram meters squared per second squared. And that plays right into the definition of kinetic energy. Because a kilogram is a unit of mass, and meters per second is a unit of velocity or speed. And if we square that, that's where we get this. Kilograms meters squared per second squared, from mass times velocity squared. So that's where that unit comes from. That's the joule. The abbreviation is a capital J. So a joule is the same as 1 kilogram meter squared per second squared. Another way to look at the joule, and when you look at the metric and SI systems of units, you see that the units are all interrelated. The joule is the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. And so that ends up being equal to a Newton, which is a unit of force, times a distance, m. And so energy was the capacity to do work, right? Work is a force times a distance. Newton is a unit of force, and the mass is the distance. The meter. The mass is the distance. I think that's the most brilliant thing I've said all day. The mass is not the distance. That's meter. Meter. So a joule is a newton times a meter, or a kilogram meter squared per second squared. And what does that make a newton equal to? If 1 newton times a meter is 1 kilogram times a meter squared per second squared, then what's a newton? It's a kilogram meter per second squared. So we do use joules in chemistry. We also use calories. You're probably more familiar with calories. A calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. A calorie is exactly 4.184 joules. That's a good relationship to know. These are metric units, so we can use prefixes with them. So a kilocalorie is 1,000 calories. It's the energy needed to raise 1,000 grams of water 1 degree Celsius. Now this calorie has a lowercase c. This is not the same as the calorie in your food. A dietary or nutritional calorie has a capital C. It's a big C calorie, and that's actually equal to 1 kilocalorie. Yeah, so when we were in graduate school, we would, you do stuff, right? So you're like, well, I wonder, it takes energy to melt ice. I wonder if you ate enough ice, could you lose weight? How many calories would you burn by eating ice? And so we would do calculations. It's not a practical way to lose weight. So these are some energy conversion factors. These top two are ones you should know. Lowercase c calorie is 4.184 joules. A big C calorie is the same as a kilocalorie, which is 1,000 calories, or 4,184 joules. The kilowatt hour could come up in a homework problem, but I won't expect you to know that on a test. Kilowatt hours is what the electric company measures energy in. And just so you get an idea for the sizes of these things, because the amount of energy to raise the temperature of 1 gram of water by 1 degree Celsius doesn't make a lot of sense. But how about the amount of energy required to light a 100-watt light bulb for 1 hour? That would be 3.6 times 10 to the 5th joules. So a joule is a small unit of energy. 8.6 times 10 to the 4th calories, 86 dietary calories. And that's only 0.1 kilowatt hours. So those are just kind of interesting.